Stress is a pressure that's applied to a object, and strain is the resulting fractional deformation of that object. A lot of objects that we see in applications in engineering, etc., are effectively one-dimensional or close to being one-dimensional, where you have a bar or a beam is some kind of rigid member that has a length that's much greater than the cross-sectional area. And so for those, we usually look at the forces that are being applied relative to that axis, relative to that long length. One of the most common types of stress and strain that we see is normal stress and strain. A normal stress and strain is a force that is normal to the cross-sectional area. It is perpendicular to the cross-sectional area of that member. And when you apply a perpendicular force, it can cause elongation or compression, depending on which direction that force is being applied. But it's not just a matter of force. Stress has to be a pressure, so this is the force being applied divided by the area, the cross-sectional area of that member. And so our normal stress here is a small sigma, and it is our normal force, the force applied to the beam perpendicularly to its cross-section, divided by the area of the cross-section. This is still a pressure, so it's still measured in pascals, where recall a pascal is a Newton per meter squared in the SI system. When you apply a outward normal force like this, it's going to stretch the end of the beam, and the beam is going to elongate from its original length. And so we're going to call that deformation, that elongation in this case, a lowercase delta. Delta is the actual change in length, the actual elongation in this case, but our strain is not the total amount of length change. It is the fractional length change, the fractional deformation that's caused by the stress. So to find the actual strain that we have, which here is a small epsilon, we have to take the change in length, change the delta, and we divide it by the original length, L0. So that is our fractional value, and a fractional value is unitless. So our normal strain is a unitless quantity. It is the change in length divided by the original length of the beam. And for a reversible strain, for us to remain in the elastic region here, the amount of deformation can usually only be around 0.1% of the original length before you start damaging and deforming that member irreversibly. So our normal strain is delta over L naught, and this is a unitless quantity because it's length divided by length. Young's modulus is the proportionality constant for normal stress strain. You may also see in your engineering classes, you may see this as the modulus of elasticity, capital E. This assumes that you have a rigid member, a rod or a beam that has, and generally that it's quite a bit longer than the cross-sectional area, the dimensions of the cross-sectional area. We're going to apply a normal force to create a normal stress. That normal force could be tensile, which leads to elongation, or it could be compressive, which leads to a compression, a loss in length. Depending on the material you have, some materials have different moduli for compression and tension. For others, it's the same value for both. You'll get the value of the Young's modulus off of a table, and it will tell you whether that value is for tension or compression or both. And the equation you're going to have is your normal stress is equal to your Young's modulus times your normal strain. Notice how this looks like Hooke's law. The force being applied is equal to a constant depending on the strength of the material times the distance that the material stretches.